So we all know that quantitative data consists of numbers. And those numbers come from measurements of some sort. And oftentimes when we collect data, it is simply going to be in its raw form, in the sense you just have a bunch of numbers laying around. For instance, let's take an example. A simple one, the amount spent on lunch by a student. So we need a sample first. So I'm just going to arbitrarily make some money amounts here. So let's start with that's plenty. So here we asked a bunch of people, a bunch of students, as to what amount they would spend on lunch. So we ended up getting those observations, and I see I put in 2 zeros there, and you may ask me, well, what does that 0 mean? That 0 simply means that students whom we spoke to simply said that they don't spend money on lunch, in the sense they don't eat lunch. So in total, we have 7, 10, 13, 14, 17, 20, 21, 24, 28 observations. So the sample size is 28. And the data that we see here is just a simple sample, and it's what we call raw data. And looking at a bunch of numbers is not going to provide us any information. So if we want to get a better picture, we have to literally get a picture, visualize the data in some form. So how do we get that? So what we have to do is we take the raw data, and we organize the data, organize in the sense group, using a frequency distribution, and use that frequency distribution to obtain a histogram. And what is a histogram? A histogram is simply a bar graph for continuous quantitative data. So we all know what a bar graph is. We looked at a bar graph with qualitative data. So when we have numbers, we just have to use a histogram. And typically histograms work well for continuous data in the sense data that are not discrete values. Last time we spoke about a stem and leaf plot. We looked at a dot plot. Those plots are good for small discrete data. But when we have continuous data, we usually go for a histogram. Now, I'm going to show you how to construct this histogram, but in practice, though, if you use Excel or if you use some statistical software, you can easily come up with this histogram in a matter of minutes. So, but I'll explain the process behind it so that you understand what you will be looking at if you created a histogram. So, so the very first step is to identify the number of bars we need. In the sense, we need to create intervals to put the observations in. To do that, we are going to come up with something called classes or bins. Think about it this way. You have a bunch of clothing items and you want to put them in different laundry baskets, and you have, say, 10 baskets lying around. So you want to put, a few items in basket number 1, few items in basket number 2, and so forth. So the idea here is to first look at the minimum and the maximum value of the data. In our case, it is 0. And it goes all the way, excuse me, it goes all the way up to $9.99. I'll just call it 10. Now, what we want to do is to divide this entire interval into pieces. So let's say I just want to form 5 different pieces, and each piece, each interval, so we have 2, 4, 6, and 8. So that would become class 1, class 2, and class 5. So we have 5 different classes. Here, the class width is simply 2. So the width of the class is 2. I arbitrarily picked a class width of 2, and the number of classes ended up being 5. But in practice, there are ways to choose classes in such a way you can see the data better. And how do we choose that? It comes with experience, depending on the size of the sample and the amount of outliers you have, and so forth. Once we identify or get a good feel for the data, we can determine the number of classes that are required to form a nice histogram. So now that I've identified the 5 classes, what I'm going to do is just add a little bit and subtract a little bit on either side to form class boundaries. So we have the amount, and I'm going to subtract 0.05 from 0. So I have minus 0.05 all the way up to 2 minus 0.05, which is 1.95. 1.95 all the way up to 3.95 and so forth. But some might say, well, I don't want to do that correction at all. I'd rather keep it as 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Either would work. So what I started with is what we call continuity correction. So when you do things manually, we want to add and subtract and adjust the boundaries a bit. But in practice, though, it really doesn't matter. What matters is in which class are you going to put a certain observation. In other words, if I have the number 2 in the data, so 2 could go either in the first class, so it could go here, or it could go there. Now that becomes tricky. Now in my problem, we don't have any integer values except for 0, so I'm not worried about it. So let's put every observation that we see between 0 and 2, the tally, in the first class. So we go back to the data. Between 0 and 2, we have 1, 2, 3, 4, 5. Next, we look for observations between 2 and 4. So we start counting. 1, 2, 3, 4, 5, 6, 7. Then we look for observations between 4 and 6. 1, 2, 3, 4, 5, 6. I believe that's it. Between 6 and 8, we have 1, 2, 3, 4, and that is all. Between 8 and 10, we have 1, 2, 3, 4, 5, 6, 7. So what we have created is simply a frequency distribution. We have seen this before with qualitative data. And that's what we call as group data as well. So frequency distribution, group data, they mean one and the same. Now that we have the frequency distribution, we can create a histogram. So between 0 and 2, we have 5 students. In other words, 5 students specified that they spend between $0 and $2. Between 2 and 4, we have 7 students. 4 and 6, we have 6 students. 6 and 8, we have 4 students. 8 and 10, we have 7 students. Come on. Okay, not put 12 over there. So we sort of see a shape. My eyes can see it. So if we can't see it, how can we sort of get to the shape? What we can do is perhaps put dots right in the middle. And we can connect the dots. So since we're talking about continuous data, I can directly connect the dots here. So instead of using a dotted line like we did last time, and that is the underlying shape of the data. So we have to look at the shape and determine an analysis that would work for the shape. Oftentimes, when people do statistics, they go wrong and give the wrong answer because they interpreted the data the wrong way. In other words, they look at a shape like this and apply a method that wouldn't work for a shape like this. So we've got to be very careful prior to choosing analysis just by looking at a histogram. So using that idea, that is what we call a histogram, what you see there. And I called it a bar graph for continuous data because we have a bunch of bars and we don't have any space between one bar and the other. There are no gaps. So, which is why we call this a bar graph. Okay, so now we can go for an example. We didn't have to create a histogram. What we have is a histogram that is provided to us. So a car salesman records the number of cars he sells each week, and that information is obtained from the past year. And that is the histogram we have. We have the number of cars sold on the x-axis and the frequency on the y-axis. In other words, you've got to be careful. We're looking at the number he sold each week. So how would we interpret it? So if we look at how many weeks did he not sell any cars at all? So didn't sell any cars would mean 0 cars. And how many times did it happen? In how many weeks did he not sell any cars? It would be 4. And that's how you should interpret it. So the number of cars sold is on the x-axis. So what is the most frequent number of cars sold in a week? So if we look at the most frequency, it is going to correspond to the tallest bar. And you can see the tallest bar happens at 4. So the most frequent number of cars he sold would be 4. So the next one is for how many weeks were 2 cars sold. So first we've got to identify 2 cars, which is right over here. In how many weeks did he sell exactly 2 cars? The height of the bar is 9. So now we have to determine the percentage of time 2 cars were sold. So what does percent mean? Percent simply means some value relative to some other value. So we're going to look at the total number of weeks that the car salesman worked. So and we could determine that simply by adding the height of each bar. So we have 4 plus 2, 6, 6 plus 9, 15, 15 plus 8, 23, 23 plus 12, 35, 35 plus 8, 43, 43 plus 5, 48, 48 plus 2, 50, 51, and 52. It looks like he doesn't get a break at all. So he works the entire year without any break. So 52 weeks. So what percent of those 52 weeks did he sell exactly 2 cars? So total number of weeks is 52. The number of weeks when he sold 2 cars was 9 weeks from part B. So the percent when 2 cars were sold is simply 9 divided by 52, which is 3/14 if we simplify it. So we can use a calculator to determine the exact percent. So it turns out to be 0.21428. So we would have 0.21428. We can round it and write it as 0.2143. So 21.43%. So 21.43% of the time, this particular salesman would end up selling 2 cars per week. Lastly, they are asking for the shape of the distribution. Most important thing. I put those dots in the previous part so that we can identify the shape. Now I'm just going to connect the dots. That is the sort of shape that we see. It is not a regular bell curve, but it sort of looks like a bell curve, but it actually is not a bell curve. It's more of a skewed distribution. So as I mentioned earlier, the purpose of a histogram is to identify the shape of data. And that's exactly what we were able to do in part D. So this is a problem on IQ scores, and they sort of made it easy for us. They gave the frequency for each class. So the distribution of IQ scores starts at a minimum value of 60, goes all the way up to 160. So first part wants to know how many students did we sample. So all we have to do is add all the frequencies that we have. So it is simply the sum of all frequencies. So 2 plus 3, 5, 5 plus 3, 18, 18 plus 42, 60, 60 plus 58, 118, 118 plus 40, 158, 158 plus 31 is 189, 189 plus 8 is 197, 197 plus 2 is 199, and plus 1 is 200. So in total, we have sampled 200 students. Part B wants to know the class width. So the class width is the same for all classes, and it has to be the same for all classes. So we just have to pick one class. Let's see. The width between 80 and 90 is 10, 110 and 120 is 10. So the width is simply 10. So each bar has a width of 10. So now we have to identify the classes and their frequencies. In other words, they are simply asking for a frequency distribution. So the classes that we have and the corresponding frequencies. We know that the smallest, the first class starts with an IQ score of 60, and each class has a width of 10. So 60 to 70. We have to go all the way up to 160. And the frequencies are given to us. So 2, 3, 13, 42, 58, 40, 31, 8, 2, and 1. And we already know from one of the previous parts, the sum of all these frequencies is 200. So all they're wanting in part C is the frequency distribution. Part A would like to know the class that has the highest frequency. If we go and look at the class with the highest frequency, that happens right here. And visually, you can identify the class with the highest frequency just by looking at the graph. The class with the tallest bar would be the class with the highest frequency. Naturally, what I picked was between 100 and 110, which is right over here. And that is the class with the highest frequency. So it would be an IQ score from 100 all the way up to 110. Which class has the lowest frequency? We're simply going to look for the class with the smallest bar or the shortest bar, which would be right here between 150 and 160. Part F would like to know the percent of students who had an IQ of at least 130. So an IQ score of at least 130 would mean 130 or more. So we simply have to start with the level or the class that says 130 to 140. So all of those classes have an IQ score of 130 or more. You can either pick that from the frequency distribution, or you can look at the graph and say, okay, 130 or more, I could simply pick that, that, and that. So it's 8 plus 2 plus 1. So we would have 11. Eleven students had an IQ of 130 or more. So the question wants to know what percent of students had an IQ of at least 130, in other words, 130 or higher. Would simply be the number of students who had an IQ of 130 or more divided by the total number of students that we have, which is 200. So if we put it in the calculator, we will get 0.055. Now, how would we interpret this number that we get, which is 5.5%? So the inference here based on the sample, only about 5.5% of students would have an IQ score of 130 or more, which is simply at least 130. So that's how we would interpret the answer that we have. Excuse me, inference simply means interpretation. How are we interpreting the answer that we just got? And the last question wants to know, did any students have an IQ of 165? Again, we can look at the frequency distribution. It stops right at 160. So there is nothing past 160. You can also look at the graph. There is nothing here past 160. So the answer would be no. So the graph that we see here is what we call a time series graph. A time series graph is pretty much a line graph. You might have used Excel or other software, and they would say, oh, draw a line graph. This is simply a line graph, but why do we call it a time series graph? If you look at the x-axis, the x-axis is time. So in this case, it's the number of years starting at 1890 all the way up to 2020. The y-axis is some measurement, and that measurement in our case is age. Age when people get married. So, or when they get married for the first time. So if we have any measurement and if we plot it against time, then we call it a time series plot, because we are plotting a series of measurements against time. So here we have two time series plots, or two time series on one plot. One is for men, which is in blue. The other is for women, it's in red. And it just shows how the age changed when people got married for the first time over the years, since 1890 all the way up to 2010. So the first question wants to know, to the nearest year, what was the average age of a man who first married in 1980? So we're looking at males. So 1980 is right over here. And the corresponding age value is 25. And similarly, they want to know for 1960, the average age of a woman who first married in the year 1960. Now, we shouldn't be looking at the blue line, because the blue series is for males. We are looking at females, so it has to be the red line. So it's right over there, and slightly over 21, just by a tiny bit. So I'm going to call it approximately 21. But when you do the homework and stuff, I think 21 would be an acceptable answer. In which year was the difference in the average age of men and women at which the first married the largest? In other words, we want to look at the gap between the male and females. So let's look at, clearly the gap is narrow over here. So we don't have to worry about that part. Doesn't matter, it's a narrow gap. Just by looking at it, it seems to me that year 1950 would have a greater gap. Let's see if that is true just by verifying. The difference in 1890 was approximately 23.5 to 26.5. So that was a 3-year gap. And the next looks pretty much the same, 26 to 23. So approximately 3 years still. That still is approximately 3 years. 25.5, this becomes 22.5, still approximately 3 years. 25, slightly higher than 25, and we have 22, perhaps 22.7 maybe. So that would be about 2.5, approximately 2.5. And over here we have 25.1 and 23, so about 2.1. And the last one over here, the distance is 21 all the way up to 24. That's approximately 3. 1950 though, we have 20.5 all the way up to 24, which would simply mean the gap is 3.5 years. So the answer would be the year 1950, and the approximate difference is 3.5 years. Now, I mean, just by looking at the graph, I was able to narrow it down to 1950, but you can always, verify the answer by doing what I just did, subtracting the age between males and females. So in which year was the difference in the average age of men and women at which they first married the least? So if you look at the curve, things are narrowing, and the narrowest part in the graph seems to me happens right here. And that would be the year 2000. And you could do the same process that we did previously with the largest gap. So the narrowest gap happens in the year 2000. And the approximate difference that we see would be 25.5 approximately here. And that is perhaps 26.75 approximately. So the gap is approximately 26.75 minus 25.5. So that would be 1.25. So we have an experiment where a basketball player is, interviewed or whatnot, and we're looking at the number of free throws she would shoot until she misses. So she's making all those throws until she misses. We want to find a relative frequency distribution, and we know what the relative frequency distribution is. It's simply the frequency divided by the total. So the total that we have if we add all the frequencies, we will get 50. And we want to know the percent of time that what percent of time, well, I'm sorry, I didn't create the relative frequency distribution. So just do it right here. (16) divided by 50. You can leave it as is or simplify and write it as 8/25, 11/50, 9/50, 7/50, 2/50. You can leave it as is, or you can simplify and write it as 1/25, 3/50, 0, 1/50, 0, 1/50. So what percent of time did she first miss on her fourth free throw? So the fourth free throw would mean she made 3 throws and then she missed on the fourth one. So the number of throws that you have to make prior to missing one would be, so successful throw, successful throw, successful throw, and the fourth throw she misses. So the number of free throws here would be actually 3. So we would have 9 out of 50. Part C, what percent of the time does she first miss the 10th free throw? So she should have made 9 of them, and the 10th she would miss. So that would actually be 0. Because if she misses the 10th free throw, that would simply mean she succeeded 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. And she missed her 10th free throw. So the number of free throws is actually 9. So that would correspond to 0/50, which is simply 0. The percent of time did she make at least 5 in a row? In other words, she made 5 free throws or higher. Which would mean everything, including 5 and above. So that, and that. So we would get 7/50 if you add them all. So a researcher with Nielsen wanted to determine the number of televisions in households. So he is looking at 40 different households, and he finds those observations. So the first thing that we want to know is if the data is discrete or continuous. We look at the observations that we have, and every observation here, there are 40 of them, they're all whole numbers. So they are discrete, they're not continuous. A hint here would be, if you read the question, it says the number of televisions. So anytime you have a count of some sort, then that would be discrete data. You can't have 1.5 televisions. You can't have 3/4 of a television. You can't have 1/7 of a television. So the data is discrete because so the observations are whole numbers. Now we want to construct a frequency distribution. So we've got to be careful here. The histogram is computed or created for continuous data. And in that case, we have classes because we don't have an individual value, rather we have a range of values because the data is continuous. In this case, though, the data is discrete. So when we create the frequency distribution, we don't have classes, rather we simply have the number of televisions and the lowest value is 0, the highest value is 5. So 0, 1, 2, 3, 4, 5. Then we have the frequency. We just have to count. So if we count, how many zeros do we have? We have 1 0. Number of households with 1 television, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2 televisions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 3 televisions, 1, 2, 3, 4, 5, 6, 7, 8. 4 televisions, I've got 1, 2, that's it. 5, I only have 1. If I add, it must add to the total number of households that I observed. So 1 plus 14, 15, plus 14 is 29, 37, 40. So that adds up to the total number of households that we observed. We want to also find the relative frequency, and we know how to find the relative frequency distribution. So that would be each frequency divided by the total. So 1 over 40, 14 over 40. If you simplify it, that is 7 over 20. 14 over 40, same, 7 over 20. 8 over 40, simplify it, you'd get 1 over 5. 2 over 40, it's 1 over 20. If you simplify, and lastly, you have 1 over 40. Part D would like to know the percent of households in the survey that have 3 televisions, exactly 3 televisions. So all we have to do is go to the row that says 3, which is row number 4. It's right here. And we get the relative frequency to be 1 over 5. It's 0.2. And you can convert it to percent and, call it as 20% if you want. Part E would like to know the percent of households in the survey would have 4 or more televisions. So 4 or more is the same as saying at least 4. So we just have to add everything that is greater than or number of households that reported to have 4 or more televisions. So in total, we had 40, and 4 or more would simply mean we have to add those 2 frequencies. So 2 plus 1 over 40, which is 3 over 40. 3 over 40 is 0.075. We'll get 7.5%. So here it says construct a frequency histogram of the data. Now, it wouldn't make sense for us to draw a proper bar here because we didn't define classes, we didn't define class widths. So the frequency histogram instead of drawing bars, I'm just going to draw a thin line. So 0, 1, 2, 3, 4, 5. So that would be the number of televisions. Y-axis is the frequency. The smallest frequency that we have is 1, and the largest is 14. So I guess I'll go in steps of 4. Number of households with 0 television is exactly 1. So that's probably right here. Exactly 1 television is 14. So 14 is right over there. Exactly 2 televisions is also 14. Exactly 3 televisions, number of households with 3 televisions would be 8. Four televisions would be 2. Five televisions would be 1. So I'm not drawing a bar, rather I'm drawing thin lines because this is discrete data. Let me put a note here. Now, I could take this and convert it to a relative frequency distribution. So the only difference, if you pay close attention, the difference between a frequency distribution and a relative frequency distribution is that the relative frequency distribution, they're all percentages. Frequency distribution contains frequencies. So if I convert each of them to a percent or a decimal value, 1 over 40 would simply be 0.025. 7 over 20 would be 0.35. 1 over 5 is 0.2. 1 over 20 is 0.05. And 1 over 40 is 0.025. And if you add all of those values, 0.025 plus 0.025 is 0.05. 0.05 plus 0.05 is 0.1. 0.1 plus 0.2 is 0.3. 0.3 plus 0.35 is 0.65. 0.65 plus another 0.35 is 1. So if you sum all the relative frequencies, it must sum to 1. We have really small values, so I am going to change the frequency to relative frequency. The smallest value that we see is 0.025 and the largest is 0.35. So I'm going to go in steps of 0.05. In other words, 5%. So 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35. So number of households with 0 televisions would be 0.025, which is 2.5%. So it's probably right over there. The number of households with exactly one television is 35%, which is right over there. The same is for 2 televisions. For 3 televisions, the number of households with 3 televisions is 0.2. The number of households with 4 televisions is 0.25. And lastly, it's 0.025. Now, I am going to connect the dots that I placed with a dotted line and not a straight solid line, because the data here is discrete. So I'm going to start at 0, dash line, dotted line. What say you? And eventually it goes to 0. And over here, the relative frequency, when I connect the dot, that's what I get. Now, pardon my artistic talents, but in terms of the shape, both of them look pretty much the same, overall shape. But what changed? The frequency histogram that we drew has frequencies on the y-axis. The relative frequency histogram that we drew has relative frequencies on the y-axis. We call this a histogram, but the bars are simply thin lines because the data is not continuous. In other words, we cannot have 1.5 televisions. We cannot have 2.25 televisions. It's either 1 or 2, nothing in between. So we were able to identify the shape, but I'm connecting it with simply a dashed or dotted line because the data is discrete. In contrast to what I did earlier with the histogram that was continuous, for instance, this one, I can draw a solid line by connecting the center points. So and that's what I would get. So that is a nice little bell curve for that particular problem. And the previous one, that's not a bell-shaped curve. If we go back here, we certainly cannot connect the dots with a solid line. We have to use dotted lines because what we have is discrete data. And they want us to describe the shape of the distribution. It doesn't matter whether we are looking at a frequency distribution or relative frequency distribution. The shape is the same. It will be the same. All we are changing is the y-axis. And you can see the data is sort of skewed to one side. So this is what we call a right skewed distribution. So majority of the households would have televisions, either none or 1 or 2 or 3. And there would be very few households which have 4 or more televisions.